So here is my rubber band, and this is my quick release mechanism, which is basically a small nut. Over here I have a nail hammered from beneath. I simply put the nut on top of the nail. Now the rubber band is in position. I put the mass over here. I have this little wooden wedge that I put on the carbon rod so that it functions as a lever system. Then with the small side, with the thin side, I put this under the nut, and then I simply push this, and there we go. So I hope that's a good enough quick release mechanism. This is the tree mass. So these are the markings for the tree mass, and that went a distance on average of about 44 centimeters. This is the foremass. This is the one mass. This is the two mass. So first of all, this is the point of release. And so this is a little closet here. When I go down, here's a ruler, the 0 mark. So I think that is pretty much aligned with the start, with the point of release. All right, let's now look at the distances. These are the markings of the one velocity. And here we have the two velocity marks. So let's take the average. So in between here, just roughly like 78.5, 78.5, and here in the middle, .56 or 56.5. These are the markings for the foremass, and on average it went about 37 centimeters. So these are the markings for the tree mass, and that went a distance on average of about 44 centimeters. Okay, so here are the results. So the one mass went a distance of 78.5 centimeters on average. The two mass went a distance of, well, mostly it landed on the 55.5 centimeters, but also once or twice it landed on 58. So when we take the average, we have 56.5. So 55.5 / 56.5. The tree mass on average landed on 44 centimeters, and the foremass traveled 37.5 centimeters. So now the predictions for the two mass is that the two mass should go 1.41 times faster or 1.41 times further. So one mass, two mass, we have 78.5 divided by 55.5, and that equals 1.41. That's perfect. But okay, if we take like the average, when we divide it by 56.5, then we have 1.389. So rounded off to 1.39, still pretty close to 1.4. I guess an acceptable error range, error percentage. The 3 mass. Theoretically, it should go 1.73 times faster or 1.73 times further than the 1 mass. So 78.5 divided by 44 equals 1.78. So the prediction is 1.73 and the result is 1.78. So a little bit of a difference there. For the full mass, it should be the square root of 4, so it should travel twice as far or twice as fast. Sorry, small interruption. So the 4 mass, the 1 mass should go twice as fast as the 4 mass, or should travel twice as far as the 4 mass. So 78.5 divided by 37.5 equals 2.09. So like almost 2.1 instead of 2. So a little bit of a difference, but yeah, 2.09 and 2. I don't know whether or not this is an acceptable error percentage. It's definitely not a perfect experiment once again. So for draft science, his prediction is that the 1 mass should travel twice as far as the 2 mass. That didn't happen. So 1.41 is the prediction for conventional science, and we almost have a perfect result for that. So I don't know for the 3 mass what the prediction is, what draft science predict for a 3 mass and what draft science predict for a 4 mass. Should it travel 3 times further for a 3 mass? Should a 4 mass travel 4 times further than the 1 mass? I don't know. Do you have any predictions for those masses with the same energy input? As far as conventional science goes, the results and the theories pretty much are acceptable. They are within an acceptable error range, I suppose.